Welcome back to the week 11 of the problem solving session for the Introduction to Fluid Mechanics course. And in this week, we will be dealing with one of the most important topics, or we will be discussing one of the most important topics, which is the cornerstone of fluid mechanics, that is the Navier-Stokes equation. We'll look into the derivation of the Navier-Stokes equation and see how they're implemented in solving different kinds of fluid flow problems. So in reality, all types of fluid flows are governed by the Navier-Stokes equation. Okay, so if I want to be more precise, I should say it is the Newtonian fluids, motion of the Newtonian fluids, that is governed by the Navier-Stokes equation. Okay, so the more generalized form would be the Navier's equation or the Cauchy momentum equation that governs the fluid flow motion. Okay, but still, since most of the fluids that we, or the engineering fluids that we use in our day-to-day life come under the paradigm of the Newtonian fluids, that's why this Navier-Stokes equation holds a paramount importance in the field of fluid mechanics. Okay, so as per our usual agenda, I will briefly go through the topics that were discussed by Professor Chakraborty in the lectures. Again, I am sorry for the delay in this week's session, but I will try to cover whatever I need to help you in solving the assignment problem and of course the exam. And I will briefly go through topics discussed by Professor Chakraborty, and then after the discussions we will go through solving some problems, some standard problems that use the application of the Navier-Stokes equation and its related concepts. Okay, so with that, let us start today's discussion. Okay, so we start our discussion with the integral form of the momentum equation. So as you know, Navier-Stokes equation is basically the modified form of the momentum equation for fluid flow motion. Okay, for fluid flow motion. So there are two assumptions that we need to keep while discussing this integral form of momentum equation. So which we have already discussed, where we are finding the differential form of the momentum equation from the integral form. That is the concept of a stationary frame of reference and a non-deformable control volume. Okay, so when we consider a non-deformable control volume, let us first consider the linear momentum conservation equation. Okay, so that's the linear momentum conservation equation. Of course, I will not go back to discuss how it is derived. It is well understood by now. We have discussed it in the past 3 weeks thoroughly, so I think it's fine by now. Then for when we apply assumption 2, that is a non-deformable control volume, we can take this time derivative inside this integral, because this elemental volume, this dV, becomes independent of the time derivative, so we can just take it inside the integration. Okay, and secondly, when we apply the assumption of stationary frame of reference, our relative velocity becomes the absolute velocity of the fluid flow. Okay, because we know that this velocity in the Reynolds transport theorem is actually the relative velocity of the fluid with respect to the control volume. That's why when we consider a stationary control volume, the fluid flow relative to the control volume becomes the absolute velocity of the fluid flow. Okay, so the second assumption results in VR to be equal to V, which is shown here. Okay, then now the important task in our hand is to understand this force, the external force that we have been talking about like for so long, but we have not deduced it. What are the types of forces that acts on the fluid flow or the control volume that results in the motion of the fluid? Okay, so because till now we have discussed about fluid statics, then fluid kinematics, understood the governing equations there, and then we started the Reynolds transport theorem. That was the onset of fluid dynamics. But still, but still we didn't discuss about the origin of these forces, like what and how these forces are uh, generated or caused, or what are types of or the forms of these forces, or how can we mathematically describe them. Okay, so that's what we'll start here. But if you recall, in the the initial weeks of our discussion, we briefly discussed about the two types of forces that may act on a fluid in a fluid flow So that was the surface forces and the body forces. Okay, we discussed it way back, but still we didn't try to connect these different types of forces and the linear momentum of the fluid flow. Okay, so it is these forces that will cause the rate of change of the linear momentum, which will inherently be understood as a net force that acts on the fluid. Okay, so the surface force, if you recall, mainly constituted of the pressure forces and the stresses. Okay, the shear stresses and normal stresses, that is basically the pressure that acts on the body. Okay, so when we deduce or the surface forces, we will be dealing with the shear stress or the shear stress tensors, and basically and of course we will briefly discuss about the traction vector that helps us to find the net force that acts on the surface, force that acts on the body on a particular direction. Okay, that was the main purpose of the introduction of the traction vector. Okay, and when we consider about the body force, for the current scenario or for the scope of this course, the only type of body force that we will consider is the gravitational force. Okay, that is the mass of the fluid. Okay, so if I just save time, or if I just try to recall, Professor Chakraborty might have taken ample amount of time to deduce this derivation, so I will not go in detail, but of course I'll just briefly go through it once so that you can understand. But it's basically the what to say, it's just basically introducing, or I must say replacing this traction vector in terms of the shear stress tensor. Okay, so basically what we do is that we replace this traction vector as a dot product of the shear stress tensor and the normal vector. Okay, that's what we exactly do here. Okay, so it's I'm just forgetting the term. What is that called? It's order reduction or something. I am forgetting the term right now. So it will basically be, if I write it here, it will basically be it's basically the same thing. Okay, and which we'll eventually see when we. So we are trying to present this in terms of a vector, just dot product vector, but it's basically a second order tensor. That's why it has an index notation as well as a vector sign. Okay, that's what Professor Chakraborty had done here, just to simplify our understanding. But I'm just trying to make you understand, because when we will be replacing this vector sign with another index, it will just turn out to be a second order tensor. Okay, I'm just trying to introduce it here right away. Okay. Similarly, the body force term is again given as a written in index notation as rho bi, where I can be like if it is a in the Cartesian coordinate system, it will be say bx by and bz. That is the body force along the x, y and z coordinate directions respectively. Okay, so this is basically the left hand side of your momentum equation. Like if I go back, say let me give it equation number, say star. Okay, say equation star. So the left hand side of the equation star is deduced as this. Okay, the sum of the surface force and the body force, where the surface force is basically the product of the shear stress tensor and written in as the form of this product of the shear stress tensor and the normal vector, and the body force term is given as as a simple source term. Okay, and the right hand side of the equation we can again take the aid of the index notation to simplify the products here. So this v can be again represented as a is in the form of index is an index notation. So we can replace this v by ui, which is again the same thing. So now when we apply Gauss divergence theorem, because see, in both of these terms, in the right hand side and in the left hand side and the right hand side of the equation, we have a surface integral and a volume integral. Okay, and if you recall, in order to transform the integral form of the Gaussian equations to the differential form, to the respective differential form, we had to have this all kind of integrations in either in the form of surface integral or a volume integral. But since we are dealing with a particular fluid molecule or a control volume itself is we are dealing in a volumetric sense, that's why it makes better sense to convert all the integrals in volume integral. Okay, so in order to do that, if you recall, we had to apply a well-known theorem known as the Gauss divergence theorem to convert the surface integral to a respective volume integral. Okay, and we will do the exact same thing here. So just one second. Okay, we will do the exact same thing here, and just one second. Just one second. Sorry for the delay. Just one second. Okay. Okay, again, sorry for this interruption. I had to take the call, so sorry for that. Yeah, so as I was mentioning, like we previously did, we converted the surface integral to the volume integral using the Gauss divergence theorem, and we do the same thing to both of these terms, that is this term and this term. So once we do that, we can write the equation on star as this. Okay, so I will give you say 1 minute to look into this equation, say equation 2 star. Okay, just look into it. If you have any confusion, you can ask, or you can, I will give you a time to look into it, 1 minute to look into it, and then let us go to the next step. Okay, so if you remember, I was saying that the vector notation shown here, say, or in here as well, left here as well. So see, let me make it clear that Professor Chakraborty found a very elegant way just to help you understand the transformation from the traction vector and representing it as a product of the shear stress tensor and the normal vector. Okay, so he was just trying to make you understand how this conversion is done, like how to replace this as this. Okay, and to do that, he just wrote the shear stress tensor in the form of a vector, like a vector in which each of its components has separate components. Okay, that's why you can see that this each term here has a component, say in the xyz direction, and this itself is a vector. Okay, and similarly he also left this velocity as such as in the vector form, so that at the end he can replace it with a index notation to complete the form the equation in the form of the he could completely write the equation in the index notation, in the form of index notation. Okay, so I was mentioning the same thing here. So he did the same exact thing. So when you go back, like of course this dot product disappears when we convert this surface integral to a volume integral from using the Gauss divergence theorem. But I hope you get the idea. So once you look from equation 2 7, when once you if you replace this vector symbol with an respective index with here and here, the final form of the equation that we have in our hand is this. Okay, is this. Okay, and this equation of is, and once you replace it, like of course with these index notations, this index this equation is known as is very popular governing equation known as the Navier's equation or the Cauchy's momentum equation. Okay, and why this equation is very important, because see, let me tell you. So Navier-Stokes equation, when we say, is just the understanding that the shear stress, this term, behaves or varies linearly with the shear strain rate of the flow field. Okay, so basically, like if we substitute the fluid as a Newtonian fluid in this equation, we will get the Navier-Stokes equation. Okay, which is of course the cornerstone of fluid mechanics. But still, this is the more generalized form of momentum conservation in fluid flow, because there might be scenarios like if you are going to take higher studies or research work, if you are going to do say PhD or some advanced research, you will deal with fluids that do not behave as Newtonian fluids. Okay, they do not show the Newtonian characteristics. There might be scenarios where the shear stress may not vary linearly as the shear strain rate, and there might have some different power loss. Okay, there might be some different power loss. Of course, that is found through experiments and analysis. So in that case, the starting point of your analysis should be the Navier's equation or the Cauchy's momentum equation, and not the Navier's equation. Okay, that's why this is a very important equation and is thus the more generalized form of momentum conservation of fluid motion. Okay, so that's the importance of the Navier's equation. But for the scope of this course, we will be primarily discussing about Newtonian fluids, and thus we will discuss about the Navier-Stokes equation. Okay, yes, and along with that, just to tell you beforehand, along with that, one of the other assumptions that we take while deriving the Navier-Stokes equation is the Stokes hypothesis. We assume that the Stokes hypothesis is valid in the case of fluid flow motion. Then only we can derive the Navier-Stokes equation from the Navier's equation. Okay, so I hope it is clear till now. So let us proceed further. Okay. So from the Navier's equation, we have, let me just read out these terms. It may sound quite repetitive, but it is what it is. Okay. So from Navier's equation, we have dou by dou t. So dou, I call dou as the partial derivative. Okay, and delta as this term, and d as the complete derivative. Okay, just to be thorough with the notations. Okay, so dou by dou t of rho ui plus dou by dou xj of rho ui uj is equal to dou by dou xj of tau ij plus rho bi. Okay, and this you can see here that there is a repeating index in both of these terms, this term and this term. So in this case, the repeating index is j, and this term the repeating index is again j. So from the Einstein's from the Einstein's index notation, if you recall from our first lecture when we were discussing about retraction vector, the repeating index in the index notation would mean that there is a summation over that particular index. Okay, so you will understand when we take one example. Okay, so let us take one example for say in the say for I equal to 1, u1 would be equal to u. Say I equal to 2, u2 would be v, I equal to 3, u3 will be equal to w. Okay, so let it be that let it be the order. Then we have, just replace I by 1, so we have dou by dou t of rho u, and yes, this term. Okay, the second term we have summation over j. Okay, So the first term ui, u1 will remain as such, it will remain u, but second term will vary as, it will vary from 1 to 3. So it will be dou by dou x of rho u, let me just write it, dou by dou x of rho u, then dou by dou y of rho uv, then dou by dou z of rho uw. Okay, and sum all the terms then. So that's what we have done here, dou by dou x of rho uu plus dou by dou y of rho uv plus dou by dou z of rho uw. Okay, similarly in the next term, this dou by dou xj of tau ij, it will be dou by dou x of, and this, let me just write it so that the confusion is removed. So I would correspond to the x component, y would correspond to, sorry, I'm sorry, it's index, right? So for I, 1 would correspond to the x component, 2 would correspond to the y component, and 3 would correspond to the z component. And similarly, this would be u, v, w, basically the x, y and z components of velocity. Okay, so so again this term we will have dou by dou x of, again the first index will remain constant, since we are dealing with I equal to 1, so it will correspond to the x component. So we will have dou by dou x of tau xx, then j would vary to 2, dou by dou y of tau xy, then dou by dou z of tau xz, and then sum all these terms. So that's what we have done here, dou by dou x of tau xx plus dou by dou y of tau xy plus dou by dou z of tau xz. So you can see the second terms are varying together, okay, plus rho bx, that is the body force term. Okay, it's just the simple source term. Okay, so this is how we can write the Navier's equation or dissociate the Navier's equation to its respective components. And similarly for I equal to 2, the equation will vary. So just an exercise, let us try to write the equation for I equal to, okay, let me just write it here, for I equal to 2. Okay, u2 would correspond to v, so we would have dou by dou t of rho v plus dou by dou x of rho vu plus dou by dou y of rho v square plus dou by dou z of rho vw. This would be equal to dou by dou x of tau yx plus dou by dou y of tau yy plus dou by dou z of tau yz plus rho by. Okay, and similarly you can write the corresponding component in the z direction. So right now the equations may seem quite cumbersome, and in reality, like if you are solving for a very generalized case, then this is the governing equation, or these are the governing equations that you need to solve, okay, to understand predict, and say even completely analyze the free flow motion. You need to solve these equations, okay. But as cumbersome these equations seems, they are as cumbersome as they seem, okay. So these are not simple equations, they are highly non-linear equations, and even after certain assumptions that we make, that is the Stokes hypothesis, the imposition of Stokes hypothesis and the Newtonian fluid, we are still left with a very, very difficult equation to solve. Even if we have 4 equations for 4 unknowns, we are left with a very, very difficult equation to solve, which is, if you know, is one of the 7 millennium problems from the Clay Institute of Mathematics, okay, which basically mean that if you are able to solve the Navier-Stokes equation in 3D form, okay, the 3D Navier-Stokes equation, and you are able to find the analytical expressions for the velocity field and the pressure field, the Clay Mathematical Institute will give you $1 million prize, and of course you will get the Nobel Prize for solving this equation, okay. Not only solving, but if you are even able to make a slight uh, advancement, or even slight advancement towards solving this equation, uh, you will be highly appreciated and be given the prize money. And of course, if the contribution is appreciable enough, you may be even given the Nobel Prize. Okay, so some of you who are quite interested in understanding this or trying to solve this may take it as your career objective or your career aim. But again, I would suggest that before diving deep into understanding these equations and solutions of these equations, I would recommend that you take the advice of an expert in that field who suggests whether these solutions are feasible or not. Okay, so after this, let us proceed. After this overwhelming discussion on these equations, let us proceed further. Okay, so let me just go back. Let me go back again. Yeah, so this is, if you recall again, this is the Navier's equation or the Cauchy's momentum equation in the index notation for the Cartesian coordinate system. Okay, so in the vector, if you write this equation in the vector form, this equation will be valid for any kind of coordinate system. But since we have already dissociated it and represented it in terms of, say, components of x, y, and z, so we are now dealing with, or we are in the paradigm of the Cartesian coordinate system. Okay, so now let us, for the sake of advancement, for today's discussion, let us keep our focus to only the Cartesian form of this Navier-Stokes equation. Now, of course, if you start from the vector form and then impose the respective vector components, you can of course derive the Navier-Stokes equation for, say, the cylindrical coordinate system and the spherical coordinate system. But for the simplicity of this course, or for simplicity, let us just focus in the Cartesian form of the Navier-Stokes equation till we derive it, and again after the derivations we will again move back to, say, the cylindrical coordinate system when we deal with pipe flows. Okay, because the cylindrical coordinate systems turn out to be the most suitable coordinate system for dealing with pipe flow systems. Okay, so just give me 1 minute. Okay, just few seconds, then we'll continue. Okay, we'll proceed further. Okay, so let's proceed further. Yeah, so if I go back to the Navier's equation or the Cauchy's momentum equation, you will see that the primary task that we have in our hand, because see, while we are solving for this Navier's equation, the primary task is to do what? To find the velocity field, because the variable that we have in our hand is these, okay, the velocity components, and the additional variable that we have is the shear stress tensor. But if you recall, in the 3D coordinates, this shear stress tensor will have 9 components. Okay, and say if we assume that since we know this shear stress tensor is symmetric, then say it has 6 independent components plus 3 velocity components. Okay, so we will have in total 9 variables 9 independent variables to find from 3 momentum equations and, say, 1 mass conservation equation. Okay, so having 9 equations and 9 independent variables and 4 equations makes the system inconsistent, right? So that's why it's again impossible to solve, right? I'm just again forgetting the term. Sorry for my lack of this terminologist. It's called, say, let me just find that term. Okay, I would like to use that term. So just give me 1 second. Okay, I'll just try to find that term. Yes. So these kind of systems are known as underdetermined systems. Okay. So yeah, I found that term. So nine nine variables. So this double underline would mean it's a second order tensor. Okay. So for fourth order tensor, it will be tau 1, 2, 3, 4 underlines. Okay. And if you want to write in this form, and four equations. So this is underdetermined. Underdetermined. If it's underdetermined, then it is impossible to solve. As simple as that. Okay. So there is, if you are proceeding with this ideology, then you will never be able to solve it. Okay, because it's underdetermined system, impossible to solve. But there can be other way around. If you are able to say find a simplified expression for tau ij in terms of velocity and say one more variable, I think you know it by now, that is pressure. Okay, so now we are dealing with, say, if you are able to dissociate these shear stress tensors in the form of, say, pressure and velocity. Okay, then you are left with 4 1 plus 3 p is a scalar and 3 velocity components. So we are left with 4 variables and 4 equations. Wow. And now the playing ground seems quite even, right? It seems it's approachable, right? It seems that it can be solved, right? And gives us mathematicians or fluid dynamicists some hope, right? System is consistent, right? It's consistent. And possible to solve. So I will not say it's impossible, but it is possible to solve, given that we have 4 equations and 4 unknowns. But again, till now, unsolved plus almost impossible. Okay, so I will keep my discussion on the complexity of solving these kind of equations to up to this, so that I do not discourage our budding scientists and engineers. But I just wanted to discuss this, about we have made progress. Of course, we have made progress. We have reduced the number of variables, say, from 9 to 4. But how we are able to do that? How we are able to do it? So we are able to do it with the help of a equation or relation, I must say, known as the constitutive relation, that basically relates the velocity or velocity gradients, if I may say, constitutive relation. So we're able to make this progress using constitutive relation. Okay, so that's where the introduction of constitutive relation is, that is relating the shear stress with the velocity gradients that basically corresponds to the shear strain rates. Okay, so our task is to find the expression for tau ij in terms of the shear strain rates, or basically the velocity gradients. So now we can dissociate. So what we found out that this shear stress tau ij can be dissociated into the tau ij hydrostatic and tau ij deviatoric. Okay. And if you see this, if you know from the definition of a matrix, okay, I'll get why you are using matrix. This is okay. So if you recall this, a matrix can be represented in the form as a sum of a symmetric and a skew symmetric matrix. Okay. So this matrix will always be symmetric. It is sum of the half times the sum of the matrix, which is transpose, and this is skew symmetric, which is half of the sum of the matrix and it's subtracting its transpose. Okay. Why was skew symmetric? If you recall, all its diagonal components are 0, and if you recall again that if you transpose a matrix, the diagonal components remain the same. So if you subtract the matrix from its or subtract the transpose of the matrix from it, the diagonal elements will become 0 and it will give a skew symmetric matrix. Okay. So using that similar identity, say if a velocity strain rate tensor, okay, strain rate tensor can also be represented as a sum of its symmetric part and skew symmetric part, and you will see that this symmetric part and skew symmetric part turns out to be one of the two important terms that we already discussed, or two important components of this of the I would say components that can be formed from the velocity gradients that we have already discussed. First is the deformation fluid deformation tensor and the rotation tensor. Okay, this is basically the vorticity tensor. Okay, so turns out like you can represent these velocity gradients or the velocity the strain rate tensors as the sum of the deformation tensor and the rotation tensor. Okay, so coming back to understand how we can find this part, the represent this deviatoric shear stress tensor, so that can be found out from the constitutive relation. Okay, because why? Because the hydrostatic part is already known, is basically represented as tau ij. You will see it is equal to minus p delta ij. Delta is the canonical delta function. We already know it from the fluid statics part. Okay, so let us proceed. Then for Newtonian fluid, and now we are coming to we are just briefly getting introduced to the Neversov equation. So for Newtonian fluid, the rate of deformation is linear. Okay, or basically the shear stress varies linearly with the shear strain rate. Okay. Just give me 1 second. So we will have tau ij is equal to Cijkl EKL. Now this term may seem quite cumbersome and you may think, sir, what are you writing and why are you writing this? Okay, so but if you recall what we have discussed in the very first class, or let me just go back today only. Yeah. So you saw that this traction vector, this is a vector and the normal vector is again a vector, but it is being mapped or being related to each other using a second order tensor. Okay, so using similar identity, when we discussed about this, we told that a first order tensor or two first order tensors are mapped with each other using as, or I can say a first order tensor is mapped to another other first order tensor using a second order tensor. Okay, so similarly with that statement we found out that we can say that a second order tensor can be mapped upon a second order tensor using a fourth order tensor. Okay, so that's what we have here. We have four different components, that's why it will be a fourth order tensor. And in general, if say I, J, K, L all have three components each, like vary from 1 to 3 each, then C, I, J, K, L in general should have 81 components. Okay, should have 81 components. And EKL here is basically the, or EKL, or if you want to represent, you can represent something like this, which we already used, is the strain rate tensor. Okay, strain rate tensor. Oof. Okay, so again there is a very extensive and a very beautiful discussion by Professor Chakraborty in the lectures. I am not quite sure whether this was kept for this course, but in, like, if you want to see the you can go to the YouTube and just type this introduction to fluid mechanics by Professor Suman Chakraborty, and you'll get the entire set of lectures. Okay, for the entire course that covers all the basic fluid mechanics portion. So there you will see that, I'm sorry, like, I didn't show this lecture, this lecture for this course, but I've taken the other course by Professor Chakraborty, so I do not know whether he has kept the derivation here or not. But if you are interested, you can go to the lectures in the YouTube. It has all the derivations there, and moreover, you can just follow the book by him, that is the Introduction to Fluid Mechanics and Fluid Machines, book by Professor S.K. Som and Professor Gautam Biswas and Professor Suman Chakraborty. There the entire derivation is done very clearly. Okay, it's very beautifully done. So you will see that I am skipping a lot of steps. I can say I am skipping all the steps, and I can leave it you as an exercise, leave for you as an exercise. So once, like, you impose certain constraints, first is, again, since tau ij is symmetric, this comes out naturally. This 81 components is reduced to 36 independent components. Okay, just give me 1 second. Yeah, so this 31 components are this 81 components are reduced to 31 independent components, imposing that tau ij is symmetric, which it is, when we found out from the conservation of angular momentum. Okay, secondly, if we impose these two assumptions, that is a homogeneous and isotropic fluid, okay, which in general is the case. So the homogeneous fluid will it mean that it is position independent. Basically, the fluid property does not change from one point to another. And isotropic fluid will basically mean that the fluid property does not change from one direction to another. Okay, and one thing again to recall, in general these two are not, they are not equal. Okay, they do not mean the other. Like, if it does not mean that if the fluid is isotropic it would be homogeneous. Okay, but again, if the fluid is isotropic in all the points in the domain, then it is inherently homogeneous. Okay, I'm just giving the extra details, but I hope you get the idea. Okay, so these are the very two crucial assumptions that are taken by Professor Chakraborty, and then he again, given these assumptions, he would simplify the form ofCijkl as a product of Kronecker delta functions. So let me again reintroduce. We have already introduced Kronecker delta function, but let me just say it again. So this Kronecker delta function is represented as delta ij, where delta ij is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. Okay, so this is the formal mathematical definition of chronicle delta function. So uses these chronicle delta functions to simplify the form of the CIJKL, and then doing repetitive steps, not I'm not repetitive steps, doing the required steps, that is a bit lengthy derivation. He finally concludes that the shear stress tensor, which was initially dissociated as the tau ij hydrostatic and tau ij deviatory, can be written as minus p delta ij plus lambda ekk delta ij plus 2 mu eij. Okay, so let me just go through each and every term here. Okay, so P here is the pressure, or to be precise, is the thermodynamic pressure. Okay, that can be found out using equation of state. Okay, so it is, this part is basically, this part is basically corresponding to the tau hydrostatic part, because the only stress that acts on the fluid when the fluid is static is the pressure, because other terms, these terms will cease to exist because the fluid is not in motion. Okay, so all the velocity components are zero, so these will be zero, so only we are left with the pressure term. The other two terms, for now, this lambda and 2 mu are just constants for you. Okay, or let me be clear again, this mu you know by now is the dynamic viscosity. Okay, which we discussed while deriving the, when we were discussing our Newtonian fluids. Okay, Newtonian and non-Newtonian fluids. Okay, but the new constant that you are dealing with for the first time is lambda. Okay, and lambda is sometimes known as the second viscosity. Okay, the second viscosity, and the value of this lambda can be found out using the Stokes hypothesis. Okay, we will see how it is done. Okay, I hope it is clear till now. Let us proceed. Okay, let us proceed further. So right now what we do is we again look into each and every term here. So we had the shear stress tensor dissociated into minus p delta ij plus lambda ekk delta ij plus 2 mu eij, 2 mu times eij. Okay, just give me 1 second. Okay, just give me 1 second. So this ekk term, so let me just start with eij. Okay, eij. So eij is, as it is shown here, eij is a second order tensor. In general, it would mean dou u I by dou xj plus dou u j by dou xi. So just to remove any kind of confusion, Professor Chakraborty replaced, say, the general ij to say k. Okay, so that you are not getting confused with this index term. So ekk would basically mean that these are the normal components. Yeah, normal components or diagonal components. So if I write, say, something like ekk, it will basically mean half of dou u k by dou xk plus dou u k by dou xk. It will again sum it up, you will left with dou u k by dou xk. So this means basically the divergence of the velocity field. Okay, so this, since there's repeating index, it will basically mean, let me write it again, it will basically mean dou u1 by dou x1 plus dou u2 by dou x2 plus dou u3 by dou x3. So it will basically mean the divergence of the velocity field. Okay, so that's what he means here. it means here. So yeah, and the other term, this second term, is just the standard strain rate tensor, okay, which represents the rate of angular deformation. But this term, dou uk by dou xk, or the divergence of the velocity field, represents the rate of volumetric strain, if you recall, okay, in the very first lectures, okay, or the early lectures, okay. I'm sorry. Yeah. So right now, till now we have made some assumptions. That is, the fluid is Newtonian. That's why we are applying the Newton's law of viscosity. Then the fluid is isotropic and homogeneous, where we used it to simplify the fourth order tensor to relate the shear stress tensor with the uh, uh, shear strain rate tensor. Okay, and to simplify the relation, we imposed the assumption of isotropic and homogeneous fluids. Okay, so now if you look into this term, okay, let me just write it. I am write the final expression for tau ij again. Okay, that we have, sorry, tau ij is equal to minus p delta ij plus lambda ekk delta ij plus 2 mu eij. Okay, so here if you just take the normal components, okay, so if you just replace j by I in all these terms and sum it up, you will get that, and divide it by 3, you will get tau 11 plus tau 22 plus tau 33 divided by 3, you will get minus p plus lambda plus 2 by 3 mu dou uk by dou xk. Okay, so as I already told you, in the hydrostatic part of the stress, this p represents the pressure, or precisely the thermodynamic pressure. Okay, and mechanical pressure from definition is the average of the normal stress components. Okay, that is tau 11 plus tau 22 plus tau 33, average it, divided by 3, you will get minus p plus lambda plus 2 by 3 mu dou uk by dou xk. Okay, and this this is the this is the mechanical pressure, and this p here is the thermodynamic pressure. Sorry, thermodynamic pressure. Okay, and you will see that these terms are separated by a factor given by this term. Okay, lambda plus 2 by 3 mu dou uk by dou xk. Okay, and the main difference between the thermodynamic pressure and the mechanical pressure is that this mechanical pressure only takes into account the translational mode of energy of molecules. Okay, the pressure generated because of the translational mode of the energy of the fluid molecules. But thermodynamic pressure takes into account all the modes of energy. It is the translational, the vibrational, the rotational, and all the other modes of energy. Okay, and but in general these two are equal. Why? Because of the Stokes hypothesis. Okay, because of the validity of the Stokes hypothesis. Okay, so if in general this p and pm are equal, it will mean that this term should be 0. Okay, this term should be 0. So if this term to be 0, then either this should be 0 or this coefficient should be 0. So let's take the first case, that is the coefficient is 0. So if the coefficient is 0, that is lambda plus 2 by 3 mu is equal to 0, then lambda is equal to minus 2 by 3 mu. Okay, this was the constant, as I mentioned, as a second viscosity, is actually equal to minus 2 by thirds of the dynamic viscosity of the fluid. Okay, when the Stokes hypothesis is imposed. Okay, and this Stokes hypothesis, or this condition, is valid, explicitly valid for monoatomic gases, and there is no further approximation required. Okay, and there is again a detailed explanation of Professor Chakraborty in the lectures, like which are the scenarios where this Stokes hypothesis is always valid. So he states that, like, this Stokes hypothesis is usually valid if the time scale of change of the fluid property is slower than the relaxation time, then this Stokes hypothesis is explicitly valid. Okay, and this is in general, like mostly this case is satisfied in most of the fluid flow scenarios that will face in our day-to-day life. But if there's scenario when the time scale of change of the fluid flow is greater than the relaxation time, is lower than the relaxation time, then the Stokes hypothesis is not valid. Okay, so these scenarios arise in very specific cases. Okay, so but in those cases, if the second assumption, if the second part of the term is zero, that is, if this term is zero, then again the Stokes hypothesis will be valid. No, then again the mechanical pressure and the thermodynamic pressure will be equal. And when can this be zero? So if you recall, this term is one of the very popular equations that we have dealt by now. It is the divergence of the velocity field. So if the divergence of the velocity field is zero, it will basically imply that the flow is incompressible. Okay, so if the flow is incompressible, or I may restate, given that the flow field is incompressible, then the validity of Stokes hypothesis is not required for the equality between the mechanical pressure and the thermodynamic pressure. Okay, so if the flow is incompressible, okay, then you do not need to worry about the time scales or different time scales of the fluid flow. Like even if the time scales of the fluid flow are lower than the relaxation time of the particular flow regime, then also if the flow is incompressible, you can confidently state that the mechanical pressure is equal to the thermodynamic pressure, and then go on with your derivation of the equations, and then we can explicitly work with the Navier-Stokes equation rather than dealing with the Cauchy momentum equation or the Navier's equation. Okay. So from Stokes hypothesis, if from the first assumption we got that if the Stokes hypothesis is valid, then lambda would be equal to minus 2 by 3 mu, and we know that mu is positive for all the fluids. Then lambda, that is the second viscosity, is always negative. Okay, so this is one of the crucial conclusion from the Stokes hypothesis. Okay, and now if you replace the value of tau ij that we found out from this extensive discussion back into the Navier's equation, okay, so we get that dou by dou t of rho ui plus dou by dou xj of rho ui uj is equal to dou by dou xj of minus p delta ij plus lambda dou uk by dou xk delta ij plus mu dou uj by dou xj plus dou uj by dou ui by dou xj plus dou uj plus dou xi dou uj by dou xi plus rho bi. Okay, so again we need to operate this differential operator on these terms individually. So if you do that, you will get that dou by dou xj minus p delta ij is equal to dou p by dou xi, and dou by dou xj of lambda dou uk by dou xk is equal to dou by dou xi of dou by dou xj of over operated over lambda dou uk by dou xk delta ij would be equal to dou by dou xi over operated over lambda dou uk by dou xk. And finally, when you operate dou by dou xj over this term, you will get two terms because there is a summation here. Then we have dou by dou xj of mu dou u by dou xj plus dou by dou xj of mu dou uj by dou xi. So now if you consider that this function u, the velocity is smooth enough, then you can interchange the order of derivatives. That is, you can take, instead of having dou by dou xj of mu dou uj by dou xi, you can have dou by dou xi of dou uj by dou xj. Then this term again, dou uj by dou xj, is again this divergence of the velocity field. Okay, so which will again be used for simplification. So if you again relate these two terms, then we will have dou by dou t of rho ui plus dou by dou xj of rho ui uj is equal to minus dou p by dou xi plus dou by dou xi operated over lambda plus mu dou uk by dou xk plus dou by dou xj of mu dou uj by dou ui by dou xj plus rho bi. Okay, sorry for this repetitive use of differential terms, but it is what it is. We have to use that for proper understanding. Okay, and this equation again, you have not yet reached the Navier-Stokes equation. This again is simplified form of the Cauchy momentum equation or the Navier's equation. Okay, you'll see why. So now here, if you impose that the Stokes hypothesis is valid, okay, we are not imposing the flow is incompressible. Okay, first assumption that we impose is that the Stokes hypothesis is valid. So if the Stokes hypothesis is valid, then lambda is equal to minus 2 by 3 mu. Okay, so if you substitute lambda is equal to minus 2 by 3 mu, then we will have this term is equal to mu by 3. Okay, so given that if you impose Stokes hypothesis, stationary frame of reference, Newtonian fluid and homogeneous isotropic fluid, you will have rho dou u by dou I by dou t. So of course you can substitute it by the complete derivative and apply mass conservation. If you apply mass conservation and simplify this term, let's try to do it as an exercise here. Okay, I hope it was done, but just let us try to do it. So it would be rho dou ui by dou t plus ui dou rho by dou t plus ui of rho uj plus, I will see whether, just give me 1 second, plus, yeah, you have to use the same term dou uj dou ui by dou xj. Okay, so if you combine these two terms, okay, so again we can write rho dou ui by dou t plus rho uj dou ui by dou xj plus ui dou rho by dou t plus dou by dou xj of rho uj. So if you recall, this is basically the mass conservation equation. So this is 0 from mass conservation. Okay, so till now we have not imposed the incompressibility condition. Okay, this is from mass conservation, and this, if you recall, this will become equal to these two terms, sorry, these two terms are equal to rho complete derivative of ui. Okay, rho dui by dt. That's what we have written here. So if you impose Stokes hypothesis, stationary frame of reference, Newtonian fluid and homogeneous isotropic fluid, you are left with this equation, the general Navier-Stokes equation, given by rho dui by dt minus is equal to minus dou p by dou xi plus dou by dou xi of mu by 3 dou uk by dou xi plus dou by dou xj of mu dou ui by dou xj plus rho bi. Okay, so this is the general form of the Navier-Stokes equation, where we start from the Navier equation or the Cauchy's momentum equation and impose the assumption of Newtonian fluid, homogeneous isotropic fluid, and the Stokes hypothesis, that is Stokesian fluid. Okay, now if you want to simplify it a bit further, considering that the flow is incompressible, that is dou uk by dou xk, dou uk by dou xk is equal to 0, that is divergence of velocity field is 0, then this equation is simplified even further. So this would be equal to 0, right? And then we can write it as dou rho times dou ui by dou t is equal to minus dou p by dou xi plus dou by dou xj of mu dou ui by dou xj plus rho bi. And if you consider this mu to be constant, then you can write this as simply as rho dou ui by dou t is equal to minus dou p by dou xi plus mu times dou square ui by dou xj or you can write this as dou xj square as well, it's your choice, plus rho bi. Okay, so this is the incompressible Navier-Stokes equation. Okay, so I hope it is clear till now. I will, and again, there was an extensive discussion of some of the standard problems whose exact solutions are known. That's why it is known as some of the exact solutions of the Navier-Stokes equations. Navier-Stokes equations. Okay, I'm sorry, I written solutions. It will be equations. But again, in order to save time, what I will do is I will deal only with one example in today's discussion, this problem solving discussion part, and then the other two examples. Okay, of course, you can apply similar understanding to uh, understand the other two problems. So here I will discuss the flow through two parallel plates. Okay, and understand different things that we can derive from the simplification of the Navier-Stokes equation. But it is the exact solution. Okay, you will see why. And the flow through pipes and the co-ed flow, both the pressure driven and the shear driven co-ed flow, you can understand from the lectures or follow the textbooks. Okay, so I will discuss this solution, this part, and then we'll directly go to the problem solving parts. Okay, I will discuss some questions, I'll give you some time to solve them, and then we can look into the solution. Okay, so I hope it sounds fine. Then let's proceed. Okay, so as I mentioned, this is the incompressible form of the Navier-Stokes equation in index notation for Cartesian coordinates. Okay, for Cartesian coordinates, because you're dealing with x1, xi, xj, xk. Sorry, x1, x2, x3 basically mean x, y, and z coordinates. So this is in Cartesian form. Okay, but again, you can also deal with the vector form. That is, if you just write this equation in vector form, you can write this equation in this form. Then this equation is again valid for any type of coordinate system. Okay, I iterate it again and again that the vector form of the equation is valid for any type of coordinate system. Okay, be it Cartesian, cylindrical, or spherical. But this index notation, at least in this case, is specifically designed for the Cartesian coordinate system. That's why this form of equation is only valid for the Cartesian coordinates. Okay. So let us discuss this first. The only example that I will take, that is flow through two parallel plates, and this again one of the very standard solutions of the Navier-Stokes equation. So I would request you to just give me 1 minute to deal with my sore throat. I have been talking for the past 1 hour, so just give me 1 minute to deal with my throat, and then meanwhile you can look into the diagram and understand all the terminologies shown here. And of course, this was there by Prof. Chakraborty, so I will not extensively discuss the diagram. Of course, I'll deal with its components and tell you about these different parts, but I'll not tell you how the different regions are generated, developed, these things. So for the sake of saving time, you can go back to the lectures, and it is discussed very thoroughly in the lectures. Okay, so I will just briefly discuss it. Okay, so just give me 1 minute, and meanwhile you can look into the diagram and its different components. Okay. So I think we can again proceed ahead. Okay, so let us look into the diagram, and I hope I'll be able to make you understand this, but let us see. So right away, if you look in the diagram, you can see two distinct regions that is being marked here. That is the developing region or the entrance region and the fully developed region. Okay. So the key difference between the developing region and the fully developed region is that the velocity, how the velocity varies. Okay. So in the developing region, the velocity is a function of both x and y. Okay. But in a fully developed region, this velocity is only a function of y. Okay. So because of the fact that in the developing region, when the fluid enters these two parallel plates, there will be a generation of boundary layer from both of the two ends of the plates. Okay. So and these boundary layers will keep on developing until they merge at a certain point. And after they merge, the flow beyond that point of merging is termed as the fully developed flow. And the characteristic is that this velocity profile would remain the same throughout the pipe. Okay, so there will not be any further acceleration or deceleration of the fluid in that particular region or in the fully developed region. But in the case of developing region, this velocity profile keeps on changing from one location to another, and see, as it is mentioned here, since the region of the viscous region the or the I can say the magnitude or the amount of the viscous region changes from location to location in the developing region. That's why to compensate or to maintain the mass flow rate, the velocity profile also changes. Okay, so I hope it is clear till now. So, or the basic takeaway, if I said it, of course, there can be very detailed analysis of the developing region in itself, and there can be it can discuss thoroughly in a separate class. But for at least this solution, it is the for fully developed flow and finding the velocity profile there in the fully developed region, our main focus should be in the fully developed region. Okay, and the basic takeaway, if you want to know, is just that in the developing region, the velocity component is a function. The velocity, the incoming velocity u is a function of x and y, but in the fully developed region, it's a function of only y. Okay, it only varies along the y direction. Okay, so this is x and this is y. Okay, so now you may ask, sir, then you're discussing about flow through two parallel plates and plate. Okay, if you consider two parallel plates, then the flow within it should be basically a 3D flow. Then why you're not mentioning about a z component? So to answer that, I will take, say, one more assumption. Okay, and the assumption is that the width of the plate is much greater than this greater than the gap between these two plates. Okay, so then what? Okay, so the thing is that if the width of the plate is much greater than the gap between these two parallel plates, then all the interesting physics or the flow behavior change along the z direction would basically be negligible. Okay, so even if there is, since the width is like so significantly large, so you can say that any kind of gradients of any property, say pressure and the velocity components, if at all there is, they would be almost be equal to zero. Okay, that's why all the interesting flow physics that occurs in this kind of scenario would be between in the gap between these two parallel plates. Okay, in this region only, along in the gap between these two parallel plates, and not along the width. Okay, because it's too large to have any kind of significant change. So the rate of change of any property is so low that we almost consider that there is no gradient along that particular direction, and that's why for width being much greater than the gap, any gradient with respect to the z component is equal to 0. Okay. And regarding the velocity components, so this flow inherently is considered 1D because there's only flow along the only component velocity that x is the x component velocity, that is the incoming flow. So let me just write it, just u. Okay. Okay. So the y z and z component velocity, that is u and v velocity components are 0. Okay. And you will eventually see why. Again, you will eventually see why there is no uh, u and v and z component velocity. Okay. So let us directly go to it. Then I will discuss this part. Let us directly go to why it is essentially 1D. Okay. So since if we consider a steady 2D incompressible flow, we will have the continuity equation as dou v by dou x plus dou v by dou y is equal to 0. Okay. I'm not explicitly saying that a v component is 0, but you will see how it becomes 0. And if you just think, it basically because of the boundary conditions. Okay. So we have that for a fully developed flow, dou u by dou x is equal to 0 because u is only a function of y. Okay. Then we have that dou v by dou y is equal to 0. Then v is not a function of y because since dou v by dou y is equal to 0, then v is either a function of y or a constant, or either a function of x or it is constant. That's why v is not a function of y. Okay. Now from the boundary conditions, we have that. Let me go back to the diagram again. Sorry for going so much to and fro. That is, you are considering the origin to be located at the center line. Okay, at the center line of these two parallel plates. Then from the center line, the two plates are a distance of h. Okay, as shown here. Okay. Then from the boundary condition, we will have that from no slip boundary conditions, velocity at say y equal to h, it will be 0 from no slip boundary condition. Then again, velocity at y equal to minus h, it will be 0 from the no slip boundary condition. Okay. If you do that, we have v is equal to 0 at y equal to plus minus h, and v is not a function of y. So v does not change with y. And since v is 0 at the walls and v does not change with y, then the only condition that satisfies both these conditions is that v has to be 0 for all y. Okay. And that's why v becomes equal to 0. So we do not explicitly say that there is no y component of velocity, but because of the boundary conditions and the fully developed flow assumption, this y component of velocity, that is the v, becomes 0. Okay. Yeah. So let us look into the governing equations now. I will leave this favorable pressure gradient part. So the basic point of the discussion of the favorable pressure gradient is that for the flow to be moving in the positive x direction, you need to have a favorable pressure gradient. Basically, if let me show it here. I will skip this discussion for the sake of saving time, but the key takeaway is that for the flow to occur from A to B, okay, in this direction, that is in a positive x direction, you need to have favorable pressure gradient, which is basically the pressure at point B must be lesser than pressure at point A. So then only it can induce a flow towards the positive x direction. Okay, or dou P by dou x should be less than 0. Okay, so that is the key takeaway. So I'll leave this part. Is basically application of boundaries equation in this inviscid region, because there we can apply it. So I'll leave this to you for understanding and for your own exercise. But that's the basic key takeaway. Okay. So now let us look into the Navier-Stokes equation. Okay. So let us start with the y component. So again, we take a generalized case where the plane may not be horizontal. Okay, plate might be inclined to a certain angle. So if that occurs, then we will align our coordinate systems along the center line of the plate. So our x and y coordinates will be now represented as this, okay, aligned with where x component, so where the x coordinate is aligned with the center line of the plate, of the two parallel plates, okay. Then say this plate is tilted at an angle of theta, then the gravitational force, again it can be dissociated into two respective components because g will always act vertically downwards, right? Then it is dissociated into two components, it is g cos theta and g sin theta, okay. Then along, if we consider the y component of the Navier-Stokes equation, you have rho dou v by dou t plus rho dou v by dou t plus q dou v by dou x plus v dou v by dou y equal to minus dou p by dou y plus mu dou square v by dou x square plus dou square v by dou y square plus rho by, okay, is the entire momentum equation along the, or the Navier-Stokes equation along the y direction. So why I say I do not say momentum, because we have applied lot of assumptions, it is the Stokes hypothesis, Newtonian twist. So once you do that, it becomes a Navier-Stokes equation, okay. It's not wrong to say momentum equation, basically again momentum conservation, but it sounds more suitable, okay. And now you can see that there are a lot of zeros that I have marked here, that most of the terms are becoming zero, but I'm not doing it from my own, like I'm not doing it so that the I'm not making it to become zero from my own, but it's because of the assumptions that we take, which is valid for this particular geometry, okay. So first is that v is 0, which we found out from the continuity equation. So v is 0, it would mean that this equals 0, v will be equal to 0, this will be equal to 0. So all these terms contain v, then all the terms in the left hand side are already 0, and this term would anyway be equal to 0 because one of the key assumptions that we take was that it was a steady flow, okay, it was steady flow. So we have on the right hand side, again these components v would be 0, will be equal to 0. Then we are only left with the pressure gradient term and the body force term, which is induced because of the gravitational acceleration, right? So you will see that the g cos theta is along the negative y direction, it is in a negative y direction, so it is minus rho g sin theta cos theta, okay. So we have dou p by dou y is equal to minus rho g cos theta, or p is equal to rho g cos theta y plus some function of x, okay. Then we have from the x component we have rho dou u by dou t plus u dou u by dou x plus v dou u by dou y is equal to minus dou p by dou x plus mu dou square u by dou x square plus dou square u by dou y square plus rho bx. And again rho bx is minus rho g sin theta because g sin theta is along the negative x direction, okay, is in a negative x direction, as you can see here. So for the first, again u is not 0, of course, but since the flow is steady, so the first term will be equal to 0. Then here also see, I am not doing like this, I am not cutting u to be equal to 0, but I am saying dou u by dou x equal to 0. Why? Because of the fully developed assumption. And again the second is I am not cutting dou u by dou y because I do not know how the velocity varies along the y direction. Of course it varies along the y direction as shown here, but you need to know how, okay. So I am not cutting in dou u by dou y as 0, but I am rather cutting v to be equal to 0 because we found out v equal to 0 from the continuity equation. Then dou p by dou x we do not know anything about it, so we will leave it as such. Then again dou square u by dou x square will be equal to 0. Why? Because dou u by dou x, if it is equal to 0, then dou by dou x of dou u by dou x will be equal to 0. So this term is again 0. This will be left as such because we do not know anything about it. It has to be non-zero. Then from the x component of the equation we have mu dou square u by dou y square is equal to dou by dou x of p plus rho g sin theta x, okay. Then p from this equation we had that it was equal to minus rho g cos theta y, okay, plus some function of x. Then if you compare, we'll have p is equal to rho g sin theta x plus some function of x, okay. P star is equal to rho g sin theta x plus some function of x. Why? Because if you see here, dou by dou x of rho g by cos theta will be equal to 0, so this term will not be there. So p star, if you consider it as p star, then p star is only a function of x, then p star is rho g sin theta x plus some function of x. Okay, so this pressure term becomes only a function of x. That's why you can write it as a complete derivative rather than a partial derivative. Okay, so you can write it as dp star by dx. Okay, similarly in the right hand side you will see that this mu dou square u by dou y square can be written as a complete derivative. Why? Because let me go back here. So from the fully developed assumption we get that dou u by dou x is equal to 0 and u is a function of x and y. So this is the case, then u should be only a function of y. Okay, so if u is only a function of y, then we can write this as mu dou square u by dou square by dou y square as mu d square u by dy square. Okay, as complete derivative. That will be equal to dp star by dx, dp star by dx. Now the thing is, we have two different terms which are complete derivatives of two different coordinates. The right hand side is a complete derivative of x, is a function of x only, and the left hand side is a function of y only. And this can only happen when both of these terms are constants. Okay, are equal to some constant c. Okay, then if we integrate this part of the equation, let us deal with this equation, the left hand side. So I hope this part is clear why both of them are equal to some constant c. Okay, so if we integrate with respect to y, let us deal with the left hand side. This, if we integrate this left hand side with respect to y, then we will have, so this left hand side can be written as mu d square u by dy square equal to c. Okay, from this equation, say equation star again, or say equation a, from equation a. Okay, then we will have that integrate with respect to y, we will have mu du by dy is equal to cy plus some constant c1. Now if we apply this boundary condition that at y equal to 0, du by dy equal to 0, because again from the condition of maxima or from the condition of symmetry, du by dy equal to 0 at y equal to 0, then from we have c1 equal to 0. And if you again integrate this equation, we will have mu u is equal to cy square by 2 plus some constant c2. Now if we apply the boundary condition at y equal to h, we have that at y equal to h, u equal to 0, then we get c2 is equal to minus ch square by 2, or mu u is equal to cy square by 2 minus ch square by 2, or u is equal to c by 2 mu times y square minus h square. And if you look into the geometry, let me go back again, this this y square minus h square can at max be equal to 0, or it will always be negative, because say if we are dealing with, say, y size somewhere here, okay, then y is less than h, okay, then y square minus h square will always be negative, right? That's why if we go here then this term is always negative, okay, and this term is positive. Like if you're considering the finding velocity along that where the fluid moves in the positive x direction, then this has to be positive. Then for this to be positive and this being negative, this term has to be negative. Okay, c by 2 mu has to be negative. And we know that c is equal to dp star by dx from equation a. Okay, let me just write it. From a, c is equal to dp star by dx. Okay, then u is equal to 1 by 2 mu dp star by dx y square minus a square, where this has to be negative for the flow to be in the positive x direction. Okay, so this is the velocity profile in the case of flow between two parallel plates. So again there is a brief discussion about finding the average velocity. So it is found out by the integration of u integrating u and over the entire area, so u integration of uda over divided by the total area. Okay, so if you do that, I'm just skipping the steps for the integration. Just substitute dA will be dy times w, a will be 2h times w, then this w will cancel out. Then if you replace this integration, since it is a symmetric function, right, you can replace minus integration of minus h to h as 2 times 0 to h, then this 2 will cancel out. And if you carry forward this integration, you will get that u bar, this average velocity u bar is equal to minus ch square by 3 mu. Okay, or c, this constant c is equal to minus 3 mu u bar by h square. Okay, and if you take the ratio of u bar over u, you will get u bar over u is 3 by 2 1 minus y square by h square. Okay, and there's one more thing that you can find out, that is the ratio of the average velocity over the okay, so just 1 second. Did I do a mistake in the integration? Yeah, that's not the integration but the notation. Yeah, it would be u over u bar, that's why I was getting confused. Yeah, sorry. U over u bar is 3 by 2 mu, 3 by 2 times 1 minus y square by h square. Okay, and there's one more thing that you can find out from this expression, that is the ratio of the average velocity over the maximum velocity. So at y equal to 0, u is equal to u max. Okay, this can be found out by 2 ways. Okay, first is if you just look into the velocity profile here. If I go back, so the maximum velocity is has to occur at the center line. Okay, that's the qualitative observation, but still, again, if you want to crudely impose it mathematically, then you can also do so by looking into the velocity profile. So here, if when will this term be at maximum? So this will be maximum only when y square, because y is always less than h. So if y is equal to 0, then this term will be maximum, right? So at y equal to 0, u should be equal to u max. Then if you replace y as 0 in this expression, you will get u max by u is equal to 3 by 2, or u max is 3 by 2 times u average. Okay, for a fully developed flow between two parallel plates. Okay, so this again one of the landmark solutions for flow through two parallel plates. Okay, then we look into the expression for the wall shear stress. So the shear stress at the wall can be found out as the value of this tau xy, or the shear stress at the wall, that is mu dou u by dou y plus dou u by dou x at the wall. So again, v is 0, so we are only dealing with mu dou u by dou y. Again, u is only a function of y, then we can replace this partial derivative by complete derivative. So mu dou u by du by dy. At the wall, it will basically be y equal to h or minus h, whatever you want. Then if you do the derivative, you will get that this shear stress equal to a constant value of ch, because both c and h are constants, and c is minus 3 mu u bar by h. Okay, so just 1 second. Yeah, because I will just write it. Why? Because c is equal to minus 3 mu u bar by h square. Okay, that's why. And again, if the minus sign you can deal with by replacing h by minus h, then you will have tau w as 3 mu u bar by h, just to not deal with negative sign. Okay, Then again you can find the friction factor, corresponding friction factor, by taking the ratio of the wall shear stress over half rho u bar square, that is 3 mu u bar by h divided by half rho u square. Then it will become 6 mu u 6 by rho 6 by rho u h by mu. Then if you just multiply 2 with both the sides, you will get CFS 12 by REH, which is again a very trademark landmark result. And this CF is called a Frenning friction coefficient. Okay, so I'm just stopping the this theory part for today's discussion up to here, because again there can be extensive discussion about flow through pipes, which is again one of the crucial results, but I will skip it for today's discussion, because I think the final discussion would be on flow through pipes, the final week's lecture. So there we can look into the derivation, and there is one more, just like Frenning friction factor, there is one more friction factor known as the Darcy's friction factor, which again is ironically used in today's discussion, but we will try to correlate. Okay, so let us now go into the Q&A part. I hope the question is visible. Let us try to solve as many questions as we can, say up to 7. Then we can end today's session. Okay, so the first question is: a sealed journal bearing is formed from concentric cylinders. Okay, the inner and the outer radii are 25 by 26 millimeter, and the length of the journal length is 100 millimeter. Okay, and it turns at 2800 rpm. The gap is filled with oil in laminar motion. Okay, again very important assumption. The velocity profile is linear across the gaps. Okay, this is also very important. The torque needed to turn the journal is 0.2 Newton meter. Calculate the viscosity of the oil. Okay, so for solving this, you need to understand, at least need to have an idea of this flow between two parallel plates where one of the plates is moving. So this is basically the result from the coed flows. For the sake of saving time, I omitted this this coed flow part, but still, since it was already discussed in the lectures, you can give it a try. Okay, just try it out from your side. All the information already given. You need to find the viscosity. Okay, try to correlate the shear stress, or try to find correlate the shear stress and the torque. Okay, try to find how you can correlate them. So this might be a bit new to you, so I will give you say 2 minutes. Okay, not because that I expected you to solve in 2 minutes, but I'll just give 2 minutes so you can try to frame the solution. Say whatever is given to you in the problem, you can write it down on the paper, try to frame the solution, and then we can look into the solution. Just for this is a new type of problem, so I would like to solve it for the first time, and then from next time onwards you can try to handle these problems. Okay, so I will just let's give it 2 minutes. So say around 6:51 I will look into the solution, and then we can go to the next question. try. It seems that nobody's answered, so let us try to solve it. Okay. So what happens is that in the case of journal bearing, okay, so let me just draw the diagram. Okay, so let me just try naming. This is RI, this is RO, the outer radius, all of which are already given, and then the shaft is rotating. Okay, the shaft is rotating between the journal. Okay, so shaft is rotating at a certain angular velocity, say omega. Okay, then and basically the shaft, if you want to see shaft is basically, shaft will basically come out from this region. Shaft will be rotating, right? And in order to have a smooth rotation of the shaft, a fluid is being kept within this journal bearing that prevents any kind of damage or corrosion to the shaft. Okay, because of this continuous rotation. That's why and this, as mentioned in the question, is asked, we are asked to model this kind of flow by taking a linear velocity profile. Okay, so this can ideally be true given the viscosity is too high, and for if the gap between these two shafts, or the shaft and the journal, is very less, in the very thin gap limit, then we can assume that the velocity profile in this case is linear. Okay, so let me just draw the velocity profile. So it will be something like linear velocity profile. Forgive my drawing, but this is what I'm trying to do. Okay, in the thin gap limit, we can get a linear velocity profile. So the outer bearing, the outer cylinder will be stationary, and the inner cylinder will be rotating because it is. Okay, I will just. This diagram is conceptually wrong, so I will just change the rotation sign. Yeah, then it is correct. Then it is correct. Yeah. So the inner cylinder is rotating because inner cylinder is basically the attached to the shaft, which is rotating. So it is generating a flow which in the thin gap limit can be understood or assumed as a co-edge flow. Okay, where which can be assumed as the upper plate is the inner cylinder, the lower plate is the outer cylinder, and the upper plate, and here hence here the lower the inner cylinder is rotating with a particular speed. Okay, so we have the shear stress tau as mu u by r. Okay, mu u by h, which is basically the formula for the shear stress in the case of co-edge flow. If you recall, I'll just write it here. For co-edge flow, tau was u was given by v y by h. That is the v is the velocity of the upper moving plate. Then tau is mu du by dy, right? Du by dy would be mu v by h, right? Similarly, so here u would be the velocity of the rotating cylinder, this is the inner cylinder in this case, then u would be Ri times omega. Okay, just the relation between the linear velocity and the angular velocity. Okay, and the gap here h would be Ro minus Ri. Okay, quite simple. Now again we know that this shear stress can also be given by the total force, the force from the shaft distributed over the area of the shaft. That will be the area of the inner cylinder. Okay. Then the and we also know that the net torque T is equal to the shear force times the inner cylinder, radius of the inner cylinder. Basically the shear force times the perpendicular displacement from the origin or the center of rotation, that is the inner cylinder radius in this case. Then we will have tau is equal to T by Ri, we'll just write that step here. Okay, so we'll have Fs is equal to T by Ri. Then if you substitute value of Fs in this equation, the value of Fs in this equation, you will have tau is equal to T by 2 pi Ri square into L. Okay, and mu is equal to Riw divided by R0 by Ri, and these two terms will be equal, right? These two terms will be equal to each other. Then mu Ri by Ri times omega divided by Ro minus Ri is equal to T divided by 2 by Ri square L, and if you substitute value of all these, you will get mu is equal to 0.0694 Pascal second. Okay, so that it seems that the time is up, but I will just take 5 more minutes if you don't mind. What I will do is I will read the question just for the sake of saving. I will read the question and go to the solution methodology part so that you understand the solution as well, and just go back, pause the lecture and try the solution out when you look in the recordings, and then you will get an idea like how to get the solution. Okay, because I also skipped many steps while finding the solution. I just wrote the solution steps for you to understand, but at least you know the solution whether it is correct or not. Okay, so let us look into the next question as fast as we can. So here, this is the correct answer. Okay, yeah. So let's look in the next question. Consider a steady, I will go a bit fast, please forgive me for that. You can read the question from the recording, and then I will directly go to solution. Okay, forgive me for that. Consider a steady, fully developed laminar flow of a Newtonian fluid through a duct of radius r. At what local radius r, the axial velocity is equal to the average velocity. Okay, so this question is again, you need to know for the formula for the expression for the velocity for flow between flow through a pipe. Okay, so I skip that part, but I have the solution here. So for velocity in a steady fully developed laminar flow through a pipe, we have u is equal to minus r square by 4 mu dp by dx times 1 minus r square by r square, where r is the local radius, small r is the local radius, and capital R is the radius of the pipe. Okay, and the average velocity of the pipe is given by r square by 8 mu dp by dx. Okay, now it is said that the axial velocity u in this case is equal to the average velocity. So if you equate both of them, you will get that half is equal to 1 minus r square by capital R square. Then r by r square is 1 by 2, or r is r by root 2, which is exactly the solution. Yeah. Then the solution in this case would be r by root 2. Okay. So I'll skip this question. This should be the solution. Like again, there is a detailed analysis of how this equation can be understood. Let us go through it once. A class of very small Reynolds number flow known as creeping flow occurs when viscous forces become dominant over the inertia forces. Which of the following might be a good approximation for a Navier-Stokes equation in creeping flow? Okay, so what happens is that let me just write it. Navier-Stokes equation can be represented as rho dou v by dou t minus delta p nebula p plus mu nebula square v plus rho g. Okay, so here it is told that for rho Reynolds number, the viscous forces become more dominant over the inertia forces. Okay, so the inertial force terms are, say here I represent it as I, and these are the viscous forces I represent as VI. and these are the body force terms. Okay, so if we assume that the body force terms are not that significant, okay, assume that condition, and it is mentioned that the viscous force dominate over the inertia forces, then the only two terms that we have in our hand in the equation would be this, the pressure gradient term equivalent to this viscous terms, okay, mu v square by v. So the governing equation that satisfies it would be this one. Okay, why? Because see, when you the ideal way of understanding this is by non-dimensionalizing the equations, which I'm not able to do for the sake of saving time. You will see that this term, this term, especially the viscous term, will have a 1 by Re dependence, okay, 1 by Reynolds number dependence. Okay, so when you do that, if Re is much lesser than 1, then this term dominates over both of these terms, okay, both the inertia term and the body force term, and that's why this has to be balanced by the pressure. Okay, that's why this would be equal to this term, or if you take in the left hand side, then delta P is equal to mu nebula square V. Okay, so let us look into the next question. Let us now look into the next question. We have the question as a soda straw. A soda straw is 20 centimeter long and 2 millimeter in diameter. It delivers cold drink approximated as water at 10 degrees Celsius, where density is 1000 kg per meter cube and mu is 1.3 × 10⁻³ kg meter per second at the rate of 3 centimeter cube per second. What is the head loss through the straw? Okay, just you look in the question. I will just so I hope, I'm sorry, screen got disconnected. Okay, sorry for this interruption. Sorry for rushing so fast, but for the sake of saving time, I have to do so. So I think I can make this one as the last question. Maybe this and the next one. Yeah, I think I can discuss these two questions, and then I think that would be all for today's discussion. Okay, so what is the head loss through pipe? Okay, so as I was mentioning, what I can do is I will take this question, but ideally this question should be in the last week's discussion, that is flow through pipe section, where we discuss about the Darcy's friction factor and their expression, where the head loss HF is given by FLV square by 2GD, where F is the Darcy's friction factor. And HF is the net head loss. Okay, that is what we will use here, but let us look into it once. Okay, so we have the average velocity for the flow through the straw as the mass, the volume flow rate divided by the area, and the Reynolds number is defined as rho times the average velocity times the diameter divided over the dynamic viscosity. So if you replace the value of u in this equation, you will get Re as 4q rho divided by pi d mu. We are doing it just to validate that our flow is laminar, so that we can apply the formula for the head loss. Okay, So we have u bar as, if you substitute the value of q, rho, pi, d and mu, we will get u as 1460, which is less than 2300. That is the critical Reynolds number for transition from laminar to turbulence. So we can say that the flow is laminar. So we can apply this Darcy friction factor. Okay, so we have HF as FL do 2GD. Okay, this is the value of friction, this Darcy's friction factor, head loss, and the relation between the head loss and Darcy friction factor. But this head loss can again also be found out by using the expression for this average velocity. Okay, average velocity, and from the expression for the expression for the velocity profile of for flow through cylindrical pipes. Then once you do so, since we do not have the value of f, we cannot use this formula, right? We cannot use this formula right now because we do not know the value of f. So we take the aid of the other formula, which is again used to find the head loss, which is given by 128 mu ql by pi rho gd to the power 4. This we will discuss in next week, but is quite relevant again, because this week we are discussing our flow through solution, the Hagen-Poiseuille flow or flow in a pipe. So it's relevant in this case also. So it is left here. So once you apply the substitute the value of mu ql pi rho g and d, you will get hf as 0.204 meter. Okay. So the final question for today's discussion is, sorry for skipping so fast. I really don't do that, but I have to cover the content. Okay, so sorry for that. The velocity profile for a fully developed laminar flow through a pipe length is given by this. Okay, so this is the expression for the velocity profile. Okay, again a quadratic dependence or the radius, this is r square dependence, where r is the radius of the pipe and r is the distance from the center line. For a fluid of viscosity mu, find the pressure drop per unit length of the pipe. Okay, so the first thing that you can do is find the average velocity. Okay, find the expression for the average velocity, because then you can because why? Because you can see that we are having a dependence of pressure drop on the average velocity. So you need to find the expression for the average velocity. So once you do that, you know that for flow through pipes you have the average velocity as 2 by r square integrated from 0 to r u r r dr. Okay, so it's basically found out as, I will give why how it is found out. Again, u bar is integration of uda over a. Okay, so u, for a cylindrical pipe, the elemental area would be 2 pi r dr divided area would be pi r square, right? So you can cancel out r and r here, pi and pi here, so you will be left with 2 times, sorry, you cannot cancel r there because it is, sorry, it's not like that. It is, sorry for that confusion. Okay, so integration from 0 to r, velocity is u, right? U, which is function of r. Okay, for fully developed flow through a pipe, and 2 pi r dr, and area is pi capital R square. So pi you can cancel out, right? Because it's constant. 2 you can take it out to the integration from 0 to r, u of r r dr over r square. So that is what we have shown here, right? Shown here, and just substitute the value of your velocity profile that is shown here, right? It's already given here. Substitute the value of u in this expression, right? Okay, I'm sorry again, I forgot the 3 by 5 factor. Okay, so once you do that, you will get that u average is 7 by 20 u naught dp by dx r square. Okay, I actually usually like to do the integration, but I was in a very rush this week, so I skipped the part. But you can try it out. Okay, it should be like that. So you'll see that you are getting a pressure gradient term in the right hand side. Okay, so it is told that find the pressure drop per unit length. Okay, so this you can write something like P2 minus P1 by L. Okay, if you do that, then just take all these terms in the left hand side or vice versa, then you will have P2 minus P1 by L, or the pressure drop per unit length, as 20 times u average divided by 7 u naught by r square. Okay, so that's what we got. So the answer would be this one, option number A. Okay. Okay, then I think that's all for today from my end for this today's discussion. There were some more problems, but I think they are quite similar. We can skip that. But the problems that we discussed today are quite important, and I think I took a lot of time in the theoretical discussion part, but those are important for creating the base for understanding the solutions of the problems that we have discussed here. Okay, so I hope I was able to clear out some doubts and help you out in solving the problems. Yeah, so okay, if you have any doubt, you can ask.
Good evening, sir.
Yeah, hello, yes,
Am I audible?
yes.
Sir, our exam are going to held in maybe in this month or next month. So, any tips or some important topics you can explain or guide something?
So okay, the thing is that there's one more topic left, that is, as I mentioned, the flow through pipes. That
Yes, sir. That is, I guess, that one is last class.
last it will be next week. It will be on Tuesday this week, right?
Yes. Yes.
Yes. So the important topics, see, it's really hard to tell. It depends on like whatever the examiner who is going to set the paper. So one thing you can do is, a good exercise for you would be to just to look into the assignment problems. Okay,
Yes, sir.
that would be a good revision scheme. Let me just stop recording, then I will continue the discussion. Okay, just give me one
Yes,
second.
sir.
Yeah.